Have you ever thought that maybe the universe is written in a language we're only just starting to figure out? I mean, all around us, in the most unexpected places, there are these hidden mathematical shapes. They're elegant, complex, and absolutely fundamental. Well, today, we're going to decode one of its most beautiful words. Just take a look at this thing. It's twisting, turning, it seems totally impossible. It doesn't have an obvious beginning or an end. It feels both organic and, at the same time, impossibly geometric. It's beautiful, it's complex, and yeah, it really does look like something you'd find in a sci-fi movie. But what if I told you this isn't alien at all? This exact structure, it's called a gyroid, is what gives a butterfly's wing that iridescent shimmer. It's the shape a soap film just naturally creates. And we're actually using it to design next-generation materials, like photonic crystals, structures that can literally control the flow of light. So that brings us to the big question, right? How did a shape so fundamental to both nature and technology stay hidden until the 1960s? And how was it only discovered by one scientist through a spectacular failure? Okay, so our story kicks off in the late 1960s. Our protagonist is a scientist named Alan Schoen, and he's working at NASA's Electronics Research Center. And his journey to one of geometry's great discoveries, well, it begins with him trying to solve a totally different problem. See, Schoen was deep in this field called graph theory, which is really just the study of how things are connected. He was trying to cook up a mathematical recipe that could take a really complex 3D web of points and lines and transform it into a predictable, contained shape. He wasn't even looking for a new surface. And then, one day, his recipe just failed. Big time. He fed it a graph, and instead of the neat, tidy shape he was expecting, the procedure just spit out this, an infinite, regular, repeating structure that he decided to call M4. By all accounts, his experiment was a complete bust. But this is where the mindset of a true innovator really shines. Schoen wasn't disappointed. He was relieved. As he put it, he'd been searching for a counterexample to his own rules for over a year. So for him, this failure wasn't an end. It was a brand new clue. And this is the brilliant part. As he's looking at his failed structure, he has this incredible aha moment. The hidden skeleton of his failure, it was built on a very specific geometric pattern, a pattern he'd theorized about years earlier, thinking it must be the backbone of some new, undiscovered surface. The failure wasn't a dead end, it was the path. So Schoen had this abstract, infinite failure on his hands. The next step was to turn that insight into a real, defined mathematical object. He'd found the blueprint. Now he had to actually build the house.
Now, to really get what he built, we need to talk about a key concept, the minimal surface. The easiest way to think about it is just a soap film. You know, when you dip a wireframe into soapy water, the film that forms will always snap into the shape with the absolute minimum surface area possible. It's nature being super efficient.
So Schoen figured out that his new shape belonged to a known family of these minimal surfaces. You had the P and D surfaces, they've been known for a century. But his new one, which he named the gyroid, or G, was different. And the key distinction, unlike its cousins, the gyroid has absolutely no straight lines and no planes of reflection. It's just pure continuous curvature. And it turns out these three surfaces are all deeply connected. You can actually bend and morph the P surface into the D surface without any tearing or stretching. It's a mathematical process called the bonnet transformation. And the gyroid, well, it exists as this perfect intermediate shape, right in the middle of that path. Okay, so this is the crucial point. If you start bending the D surface towards the P surface, you get a whole family of related shapes. But at one and only one precise angle, about 38 degrees, the surface just magically resolves itself into the gyroid. It becomes the single version in the entire family that doesn't intersect itself. It is, in a word, mathematically perfect. Now, this discovery wasn't just some mathematical curiosity. Once Schoen defined the gyroid, scientists started seeing it everywhere. It turns out this accidental shape is one of nature's favorite building blocks. Looking at these incredible sculptures, you can really appreciate its structure, right? The gyroid divides all of space into two separate, intertwined mirror image labyrinths. You could literally walk forever through one tunnel system and never ever cross into the other, even though they are perfectly entangled. It's this perfect blend of separation and connection. And that unique structure is exactly why it's so useful. It's got a super high surface area and all these interconnected pores, which makes it the ideal template for everything from the light-scattering structures in butterfly wings to self-assembling polymers in chemistry. It's even been theorized to exist inside neutron stars, in a phase of matter they call nuclear pasta. Wild, right? So, what can we take away from this story, besides just some fascinating geometry? Well, Schoen's path to discovery holds a really powerful lesson for anyone trying to innovate, whether you're in a lab, a classroom, or even an art studio. The path to discovery here is pretty clear. First, you've got to embrace the unexpected. Schoen's failure was the most valuable piece of data he ever found. Second, connect different worlds. He drew from math, sure, but also from architecture and art. Third, make your ideas real. His physical models and those soap film experiments were what made the abstract tangible. And finally, collaborate. Discovery is a team sport. Ultimately, the gyroid reminds us that the line between science and art, between rigorous mathematics and just intuitive beauty, is incredibly thin. This is a mathematical proof you can hang in a gallery. It's a testament to the fact that discovery so often lies right at that intersection of discipline and imagination. It really makes you wonder, doesn't it? If a shape this fundamental could hide in plain sight until 1970, what other beautiful, essential structures are all around us right now, just waiting for a curious mind to stumble upon them? Maybe even through a lucky failure. What patterns are you going to find?